Hey everybody, Corey and Victoria here. We are the Professors DuBois, and in this lecture we're going to talk about solutions and solubility.
So what are solutions, right? I want to impress upon you that solutions are homogeneous mixtures. So if you don't get anything else today, know that solutions are homogeneous mixtures. They're completely the same throughout, but they are mixtures. So something has been dissolved in something else, and we call the substance that's being dissolved a solute, and the substance that's doing the dissolving as the solvent. We're going to work with water mostly as our solvent. It's the universal solvent. But there are other solvents, and you might have heard some of these words. You might have heard tincture, and tincture is when the solvent is an alcohol. We also have organic solvents and even some solid solutions. So solutions don't have to be a liquid. We usually think of that as the only type of solution, but air is a solution of gases. So it's a homogeneous mixture of different types of gases. So I want to also point out this picture over here where the solution, you can see it is colored. So sometimes solutions are colored, but they're transparent and they are uniform all the way throughout. So the second test tube here shows that we have some suspended solid and some that's starting to settle out. And if we let this settle for even longer, all of that solid could potentially fall right down to the bottom of the test tube. So we have a suspension here in the middle, but our solution is the one on the left.
Okay, so when we dissolve something in water, so we're going to try to make an aqueous solution. You'll see that term aqueous represented with a little AQ. There's a couple different scenarios that can happen. So scenario one, it could break up completely and totally form ions. So this would have to be an ionic compound. And notice this term, it says 100% dissociation. That's specific to forming ions in solution. So dissolving and dissociation are very similar, but an ionic compound can dissociate where a molecular compound can only dissolve. Ionic compounds can dissolve and dissociate. Scenario two, we could dissolve completely but only break up into a few ions. So again, we would have to have an ionic compound or an acid.
I was going to add that at the end. So some molecular compounds that are acids can break apart into ions as well, and we're going to get there.
Scenario three, we can dissolve completely but don't form ions. So no dissociation. These would be your molecular compounds that are not acids. Scenario four, a small amount dissolves. Last scenario, nothing dissolves, doesn't dissolve at all.
Right. So number 5 would be like, we call that insoluble. Number 4 we'd call maybe slightly soluble. And then the first 3 cover what happens if it dissolves. It's soluble, but it may or may not break apart into ions. So we have 2 different words here: dissolution, dissolving, and dissociation, which is breaking apart into the ions. So here's a picture of the representation of sodium chloride being dissolved in water. So we have our solid here, our sodium ions and our chloride ions held together in that crystal matrix. And then we have water molecules here with the red and white, and they can work their way in, they can be attracted to those ions, and they can pull those ions right apart. And then the ions are very far apart when they're in the solution. That distance has increased from that closely knit ionic structure here that you see. And we represent this with a chemical equation where we have the solid going to AQ. We mentioned that before, that aqueous, when it's in solution, these ions are dissolved in water.
So sugar is a molecular substance. It does not form ions, but it does dissolve in water. So what happens here is very similar. The water molecules can kind of surround this sugar crystal, and they can kind of gang up and pull apart actual discrete molecules of this sugar. So each of these, it's like a 6-sided structure there is your C6 H12O6 is what that's showing. So we're not forming ions here. We're just breaking apart this crystal into individual sugar molecules. So we are dissolving, but there's no dissociation here. We aren't forming ions.
Dissolution without dissociation. Okay, so back to dissolution, just dissolving. How would we know if a compound is soluble or not? So you're on an exam, you have to know if you have to put the little AQ or if you have to put the little S, which means solid. And how do you differentiate that? If it's a molecular compound, like the sugar that we just mentioned, so it was made up of all nonmetals, molecular compound, it must be polar in order to dissolve in water. We haven't taught you polarity yet. We're going to get there, but we haven't yet. So suffice it to say that we will tell you if a molecular compound is polar or nonpolar. If it's polar, soluble. And that's a little bit, it's a little bit simplistic, but that's okay for right now. Ionic compounds are governed by some solubility rules. So we've been able to come up with a table of general rules for these compounds, and we'll give you this table, and you have to be able to read the table. So we're going to get into that right now. Know that there is really a spectrum, and we have soluble, slightly soluble, insoluble. So we've just made the cutoff somewhere, and with this table we're saying it's either soluble or insoluble. And actually later on in the semester or in this course, you'll learn that there is a spectrum and how to know more about solubility. But right now for ionic compounds, it's either soluble or insoluble, and you have to look at the table in order to know. Another thing is if it's an acid, it's soluble. That's a really good thing to know.
Okay, so here's the table, and we've got all the answers on here.
Oh my goodness.
So
let's get rid of those right now. Got all excited.
So this table will be provided. There are you can find similar tables. This is the table we'll use in our course, and you'll see it's they didn't make a real good distinction, but you'll notice the top part of the table says soluble ionic compounds, and the bottom part says insoluble ionic compounds. So it's really important that you can make that distinction. And if you look, what they're showing, it's mostly anions or negative charged ions. So it's when you have a compound, it's good to start with the anion, try to find the anion, and determine if it's under the soluble ionic compounds or the insoluble. And then lastly, we'll look at the cation and see if that's one of the exceptions. So it could be a soluble anion, but maybe the cation that's with it makes it an exception, and what that would mean is it's insoluble. So I'm looking at the first compound. This is strontium carbonate. So my anion is the carbonate ion. So I go to my chart and I find it. It's down at the very bottom. So the carbonates are typically insoluble. Well, this is strontium carbonate, so let's see if that's an exception. My exceptions are sodium, potassium, and the ammonium, not strontium. So there's no exception here. This is an insoluble ionic compound. Up next is the magnesium fluoride. So I'm going to go to the anion, which is the fluoride ion, and that one falls under the soluble ionic compounds. Now again, we have to look for the exceptions. So I go to the right, and the exceptions are calcium, strontium, barium, and lead. And magnesium is not one of the exceptions, so that's soluble.
And you would indicate soluble with a little AQ.
In insoluble, you would indicate with an S, which is
solid.
It means solid, and it's a little bit tricky.
It is.
Barium hydroxide. So I'm going to start looking at that hydroxide ion. That's the OH minus, and I find that's under the insoluble ionic compounds. Well, let's look at the exceptions, and sure enough, barium is an exception. So hydroxides are typically insoluble, but a barium hydroxide is soluble. That one's actually soluble. Tricky. Lead sulfate. Again, the sulfate ion, SO4. That's in the soluble category. Last one of the soluble categories. That doesn't mean anything.
Nope.
But let's look for our exceptions. Do we have lead as an exception? We do. There's the lead ion right there. So this is not soluble. The sulfates, usually are, but there are some exceptions. Lead sulfate is an exception. That is insoluble. Ammonium sulfide, be careful here. Sulfide, that's our sulfur ion, right? Sulfide ends with IDE. So ammonium sulfide, I find my sulfide ion that's down near the bottom. That's an insoluble ionic compound, the sulfides. Well, let's look for the exceptions. And sure enough, ammonium, that's the NH4 plus, that is present. That is an exception. So this is soluble. Usually sulfides are not soluble, but this is an exception.
Soluble, we'd put little AQ.
Okay, this last one is a bit of a trick question, and I'm going to kind of fall for the trick. So I've got H3PO4. I know I've got a phosphate anion. That's the PO4. This is insoluble, and if I go look to my exceptions, I do not find a hydrogen, which would lead me to think, oh, this is insoluble. But this is incorrect because this is not, first of all, it's not an ionic compound. So this chart only works for ionic compounds. And you may recognize this as an acid because it starts with the hydrogen. So this is actually an acid, and we said before, all acids are soluble. So be on the watch out for those acids. They're always soluble. You don't even need a chart.
We put that in there because this is a common problem. This is a common mistake that's made. You'll see a carbonate or a phosphate, and you'll look to this as if it were an ionic compound, and if it was phosphoric acid or carbonic acid, then it's not this chart. It's not ionic, so don't look at this chart and say that it's insoluble, when in fact it's an acid and it's soluble, and they're always going to be AQ if they're in the presence of water.
All right, so we got some practice here for you. A few different compounds. Notice a couple of these are in words. You'll have to write the compound from the words, silver chloride, and that last one, strontium sulfate. So what you need to do is start with your anion and see if you can determine using this chart. You'll always have this chart if these are soluble or not.
Pause the video and give them a try. Here comes the answers. There they are. All right. There's the answers, so hopefully you can use this table. It's really important that you can use this table and determine if things are soluble or insoluble. It's not just an effort in determining if it's soluble or insoluble. We're going to be predicting reactions, predicting products, and we have to determine if they are soluble or insoluble to go to the next step. So this is not just a be-all, end-all, just determining if it's soluble or not. We're going to be using this as we move forward. So make sure you get familiar with that table.
Yeah, we'll use that chart for a while.
We will. Yeah, it is. It's.
All right, remember, this is a place to learn chemistry where you matter. Thanks for tuning in.
Take care, guys.